In the previous video, I did a demo to try to motivate the idea that there can be a conserved quantity associated with rotation. In this video, we're going to come at this question from a different angle by making an analogy with a conserved quantity that we already know about. To be specific, we have already learned in this class about conservation of momentum. We have already seen how momentum is defined. Here's the idea. If we have an object with mass m moving at velocity v, then the object has a momentum vector p, which points in the same direction as the velocity vector. The momentum vector of the object is defined to be the mass of the object multiplied by the velocity vector. We have already learned about conservation of momentum. Conservation of momentum says that if no outside forces act on a group of objects, then the total momentum of that group is constant. What would be the rotational analog of this statement? The rotational analog of force is torque. Is there a rotational quantity which is conserved when no outside torques act on a group of objects? There is such a quantity. It is called the angular momentum. The symbol we use for the angular momentum is capital L. Now, what would be the expression that we use to calculate angular momentum? Here we're going to use an analogy with the regular momentum that we learned about earlier in the course. The first factor in the regular momentum is the mass. So what is the rotational analog of the mass? Well, mass describes how difficult it is to change the velocity of an object. What describes how difficult it is to change the angular velocity of an object? That would be the moment of inertia. So moment of inertia is the rotational analog of the mass. What would be the rotational analog of the velocity? That would be the angular velocity. So we define angular momentum as the product moment of inertia times angular velocity. One more thing I want to mention here is that the angular momentum can be positive or negative. Why is it that the angular momentum can be positive or negative? The angular momentum can be positive or negative because the angular velocity can be positive or negative. We say that an object has a positive angular velocity when it is rotating in whatever we define to be the positive direction. So in this figure here, I have defined counterclockwise to be the positive direction for rotation. So if the object is rotating counterclockwise, we would say that it has a positive angular velocity, and therefore it would have a positive angular momentum. On the other hand, if the angular velocity was negative, which in this case would mean that the object is rotating in a clockwise sense, that would mean that the angular momentum was negative as well. To illustrate the formula for angular momentum, we're going to do a quick example problem where we calculate the angular momentum of a cylinder which is rotating around an axle which passes through the symmetry axis of the cylinder. I've given the mass of the cylinder as 2 kilograms and the radius as 15 centimeters. And notice that the cylinder is rotating at 200 revolutions per minute in a clockwise sense, even though I have defined counterclockwise to be the positive direction for rotation. So let's start. We have from here that the angular momentum is equal to moment of inertia times angular velocity. The moment of inertia of a cylinder rotating about its symmetry axis is 1/2 the mass of the cylinder times the square of the radius. So that's the moment of inertia. The angular velocity is given here as 200 revolutions per minute. However, the rotation is in the clockwise sense, and we have defined counterclockwise to be the positive direction. So we're going to take the angular velocity to be minus 200 revolutions per minute. Going to the next line now, let's make our substitutions. We have 1/2 mass 2 kilograms. It says radius 15 centimeters, but I'm going to convert into meters, so 0.15 meters squared. For the angular velocity, we have minus 200 revolutions per minute, but we would like to get this into radians per second. To convert from revolutions to radians, I put in a conversion factor. A revolution is equal to 2 pi radians. A minute is 60 seconds. Notice the cancellations here. Minutes cancels minutes, revolutions cancels revolutions. When I put everything into my calculator, I get angular momentum equals minus 0.47. Now, what about the unit? I have kilograms times meters squared over seconds. Now, what about radians? Remember that radians is not a real unit. Radians is in there to remind us that we are measuring angle in a particular way. However, radians is typically dropped when we go to a dynamic quantity such as angular momentum. So we're just going to say that the angular momentum of that cylinder is minus 0.47 kilograms meters squared over seconds. Now we can return to the question which I posed earlier in the video. Is there a rotational quantity which is conserved when no outside torques act on a group of objects? Well, you can probably see where this is going. There is such a quantity, and it is the angular momentum. This brings us to the principle of conservation of angular momentum. Conservation of angular momentum says that if no outside torques act on a group of objects, then the total angular momentum of that group is constant. We can express this as an equation as well. If we have a process where no outside torques act on a group of objects, then the total angular momentum at the beginning of the process equals the total angular momentum at the end of the process, and that is something we can express by saying total angular momentum initial equals total angular momentum final for a process where no outside torques act. In the next video, we're going to solve an example problem using conservation of angular momentum.